for dynamic analysis, response spectrum method, and we will follow ASCE 716 code or IBC 2018 code. The whole session is divided in 3 segments. First, we will discuss about some common terminology used in different chapters of ASCE 716 code for seismic analysis. Next, we will cover the clauses mentioned in this code to perform response spectral analysis and how to use response spectral load instead, with a discussion on relevant seismic parameters. And finally, we will use a real Stead model and demonstrate how to apply response spectral load along with generation of seismic load combination cases. Now, I hand it over to Sudeep. He will discuss the first 2 segments, code provisions and the Stead implementation part.
Welcome to this session on the response spectrum analysis to IBC 2018 or ASCE 7 2016 code. As most of you would know, IBC refers to ASCE for the seismic specifications. So any reference to the code in this session maps to the ASCE 7 2016 code. But before we start, let us discuss or list the exclusions from this session. In other words, let us list the topics that we are not discussing in this session. Number 1, we are not considering the effect of vertical vibration. Number 2, we are not considering the P-delta effects in a response spectrum analysis. Number 3, we are not discussing on the estimation of the drifts due to seismic motions. And finally, number 4, we will not be considering the structures that are located in site class E and site class F. In this context, let me go on a bit more about the site class. Site class would refer to the type of the soil in the concerned site and which is characterized by the average shear velocity, the average standard penetration resistance, and by the average undrained shear strength in the top 100 feet of the soil. Please refer to table 20.3-1 of the code for further details on the site class. Now let us start discussing about the various terminologies of the code. We'll start off by discussing about the maximum considered earthquake, MCE in short, followed by the mapped acceleration parameters. The MCE in the ASCE code is defined in 2 ways. MCE with a subscript G, hereafter referred to as MCEG, and MCE with subscript R, hereafter referred to as MCER. MCEG is the most severe earthquake effects on the structure due to the peak ground acceleration conditions and without being adjusted for the targeted risk. MCER is the MCEG but which has been adjusted for the targeted risk. That is, the severe earthquake effects on the structure which has a targeted risk of exceedance and which is a probability of 2% exceedance in 50 years. Now let us discuss the terms S with a subscript S and S with a subscript 1, which are called the mapped acceleration parameters. We will hereafter refer to them as SS and S1. As you can see in the picture, 2 single degree of freedom systems of period 0.2 seconds and 1 second has been clamped to a rock in a specified site. These systems are 5% damped. The MCER response of these systems to earthquake in that region or an average of earthquakes around that region is what is termed as SS and S1. Now it is to be noted with caution that the rock type of site is just a very loose way of putting it. The code is very precise in the site type which is used to determine these parameters. The code has mentioned that the site we are talking about used to determine SS and S1 lies at the border of site class B and site class C with the average shear velocity of 2,500 feet per second. To give you an idea of what site class B and site class C is, we will refer to table 20.3-1, which says that site class B is made up of rock and site class C is made up of very dense soil and soft rock. So you will have the SS and S1 parameter determined in a site that is in between these two conditions. However, the chances that our site conditions would exactly match with the one described is very remote. So we need to modify the values of SS and S1 to suit the site conditions we are concerned with. Thus, SS needs to be modified with the short period site coefficient FA to give the value of SMS. The FA value is obtained from table 11.4-1. Similarly, the S1 needs to be modified with the long period site coefficient that is obtained from table 11.4-2 to give the value of SM1. Now, as I've already mentioned, that SS and S1 are obtained from the site representing the border of site class B and site class C. So the FA and FV parameters of site class B will be little lesser than 1, while the parameters of site class C will be little over 1. In case the site represents consistency with site class B, but velocity specific measurements have not been made, the code permits to take the value of FA and FV as 1. Once we have modified the MCER parameters for the site effects, we need to obtain the parameters relevant to the design-based earthquake. The code suggests multiplying the MCER parameters modified for the side effects SMS and SM1 with 2/3. The design-based earthquake generally corresponds to a target risk of 10% exceedance in 50 years. The code calls this as the design spectral acceleration parameters SDS and SD1. These design spectral acceleration parameters are used to calculate the design spectral acceleration using the equations as you can see on the screen. The spectral acceleration values, when plotted against their time periods, gives the design response spectrum curve. Risk-targeted MCER response spectrum curve can be obtained by multiplying the spectral acceleration ordinates by 1.5. Now this is the design response spectrum curve that we have obtained. You can see that the spectral acceleration is constant between the periods T0 and Ts. Ts is calculated as the ratio of SD1 to SDS, while T0 is 0.2 of that ratio. Now, if you think carefully, with softer and softer soils, the T0 and Ts would be shifting right, and so would be the flat portion of the design spectrum curve, which represents the highest spectral acceleration. Now, this is the acceleration domain of the response spectrum curve. The spectral acceleration in this region would be equal to SDS. Ts also marks the point of shift from the acceleration domain to the velocity domain till TL. In this region, the spectral acceleration is represented as SD1 by T, or the spectral acceleration in this domain is inversely proportional to the period. TL again marks the shift from the velocity domain to the displacement domain. In this domain, the spectral acceleration is given by SD1 into TL by T square. Thus, it is the inverse, or rather it's inversely proportional to the square of the period of the structure. We are now ready to start speaking on how to execute the response spectrum analysis in Stat Pro. But before that, it is important to know about a couple of factors which would be needed at every step of performing the seismic analysis. Number one, we need to know about the risk category, which is based on the use or the occupancy of the structure and which is to be obtained from table 1.5-1. Number two, based on the risk category, you also need to determine the importance factor of the structure from table 1.5-2. And finally, number three, the seismic design category, determined from table 11.6-1, which depends on the risk category and the value of SDS.
We have a poll questions for you. So we just want to know whether you are using the latest Stat Pro Connect edition or not. So please cast your vote for the correct answer. As you know, there are several latest features. Those are implemented in Stat Pro Connect edition, like the ASCE 716 code, which was previously not available in the V8i version. and already been implemented in the Stead for Connect Edition. So that's why we are asking whether you are using the Connect Edition version or not.
Now that we have discussed about the various terminologies of the code and what they mean, and also about the response spectrum curve and its characteristics, we are now ready to focus on how we will specify the response spectrum specification in Stead. So here is how the IBC response spectrum specification looks like in the command format. In our demonstration section, we will show you how you can specify the response spectrum load using the graphical user interface. In this section, we will discuss about various parameters that constitute the IBC response spectrum specification. However, we will exclude the parameters that are common to the custom response spectrum specification and which has been discussed in details in our last episode on the same. We also need to remember that the mass and the stiffness modeling are a prerequisite for the response spectrum analysis and which has been dealt with in details in the last two sessions. So we will start off by discussing the torsion specification and the associated de-eccentricity and the eccentricity commands. We have listed the clauses, as you can see, to which the torsion, de-eccentricity, and eccentricity parameters are related to. In short, we call the de-eccentricity as the DEC command and the eccentricity as the ECC command. To understand the applicability of these terms in the response spectrum specification, let us consider the picture of the rigid diaphragm on the screen. The green point on the diaphragm is the center of mass and the red point is the center of rigidity. The distance between the 2 points is called the natural or inherent eccentricity in the diaphragm. Now let the dimension of the diaphragm perpendicular to the direction of the earthquake force be L. Now when the earthquake force hits, the diaphragm experiences the force through the center of mass and resists it through the center of rigidity. This would result in a torsion in the diaphragm about the vertical axis coming out of the screen towards you, resulting in additional shears in the lateral load resisting elements. However, from the design point of view, the natural eccentricity needs to be amplified to consider the effects of a shifted center of mass due to construction or to cater for the effect of rotational components of the ground motion, resulting in additional torsional effects on the diaphragm. The additional eccentricity is called the accidental eccentricity, which is 5% of the lateral dimension perpendicular to the earthquake force, and the resultant torsion is called the accidental torsion. Thus, the center of mass is shifted in the positive direction by 5% of the lateral dimension L and is reflected by the parameters DEC equal to 1 and ECC equal to plus 0.05. Then the center of mass is shifted in the negative direction by that same amount. The DEC and ECC parameters are then specified as 1 and minus 0.05 respectively to account for this condition. The default values of DEC and ECC are 1 and 0.05 respectively. So if you specify the torsion parameter but do not specify the DEC and ECC parameters, Stead would not consider them as 0 but would consider them as 1 and 0.05 respectively. If you have the structure which has been designed as seismic design category B, you would need to consider the accidental torsion only if you have a type 1B irregularity, which is the extreme torsional irregularity. However, you need to consider the accidental torsion irrespective of type 1A or 1B irregularity for structures assigned to seismic design categories C through F. In a dynamic analysis, you would not be required to consider the effect of torsional amplification. The next parameters to consider are the direction factors in the two lateral direction X and Z. In this discussion, we are not considering the vertical direction factor Y. Again, in this slide, we see that the reference clause number of the ASCE code has been mentioned in the heading. You can see a light image of the plan of a building with a positive direction of the x and the z-axis mentioned at the left bottom of the screen. So if the earthquake force is to be applied in the positive direction of the x-axis, x equal to 1 needs to be specified. X equal to -1 needs to be specified for the negative direction of the x-axis. Similarly, z equal to 1 for the positive direction of the z-axis and z equal to -1 for the negative direction of the z-axis. However, specifying the +1 or -1 for the direction factors will not be enough for the response spectrum specification as per the ASCE code. The code requires that the force be augmented by the importance factor and be reduced by the response reduction factor. We already have spoken about the importance factor in our previous slides, but we have not discussed about the response reduction factor. The code requires that the structure be designed for the forces that is required to resist elastically and would resist the rest of the earthquake forces to plastic deformations. So the response reduction factor is a function of the ductility of the lateral force resisting system. Theoretically, the response reduction factor can be different in two directions. So the direction factor would need an incorporation of the factor I by R in each direction. Now, considering what we have learned till now, let us see how the response spectrum load cases will be specified. We will not be considering the negative direction factors, and we will be considering them through load combinations. So we see that we have specified the response spectrum cases thrice in each direction, x and z, making 6 response spectrum cases. So why do we need 3 in one direction? Well, let us look closely at the spectrum case. In the first spectrum case in the x direction, we specify the ECC as plus 0.05, where the equivalent torsional moment due to shifting of the center of mass in the positive direction of the x-axis would be considered. Thus, we would specify the DEC equal to 1 and ECC equal to 0.05. In the second response spectrum case, we specify the ECC as minus 0.05, which will consider the equivalent torsional moment due to the center of mass being shifted in the negative x direction. And thus, we specify the DEC equal to 1 and the ECC parameter as minus 0.05. And finally, we will consider the response spectrum case in the x direction with no torsion specification. Why do we need this case? We would require this case if our structure is assigned to the seismic design category C through F that has a non-orthogonal lateral load resisting system. We would also require this case in the combinations to be considered for the common members of the multiple load resisting systems for the structures assigned to SDC D through F. We will discuss this in more details when we will discuss the direction of the loading. And similarly, we would specify the DEC and ECC parameters for the response spectrum cases in the Z direction. Now let us talk about the missing mass parameters. This was discussed in details in the last session on the custom response spectrum specification. However, we will quickly mention what ASCE recommends for the missing mass. The relevant parameters we'll now discuss will be the MIS and the ZPA parameters. Ideally, you are required to consider all the modes to ensure a 100% mass participation in either direction. However, this does not seem to be practical for several possible reasons. Thus, the code goes on and permits the use of 2 further options. If we have rigid modes in the analysis, we can do a dynamic analysis for all the flexible modes, while all the rigid modes can be considered in one single rigid mode for static analysis to ensure a 100% participation. The rigid mode defined in clause 12.9.1.1 as the modes having a period less than 0.05 seconds or frequencies higher than 20 Hz. The combined rigid mode is the missing mass mode in stat terminology. We will need to define the Miss ZP-A20 to read out the spectral acceleration from the response spectrum curve corresponding to the 20 Hz frequency or 0.05 second period. This value will be very close to the peak ground acceleration because of the rigidity considerations. On the other hand, you can specify the value of spectral acceleration for rigid modes directly as the F6 parameter after the terms MIS. However, attaining the rigid modes is not always easy unless you have a very stiff structure or if you are considering the vibration in a very stiff direction only. As such, the code in the same clause permits ensuring at least 90% mass participation in the orthogonal horizontal directions. Finally, we'll discuss about the seismic parameters that has been talked about in details in our ELFP session or the equivalent lateral force procedure session. But here, this pertains to the response spectrum specification. SS and S1 indicates the mapped acceleration parameters that we have discussed a couple of slides back, while the lat and long means the latitude and longitude from which the MCER parameters can be retrieved from the maps in Chapter 22. ZIP also indicates the location from which the SS and S1 parameters can be identified from the maps. So either we specify the ZIP parameter or latitude longitude to identify the SS and S1 parameters, or we can specify the value of mapped acceleration parameters directly through the SS and S1 parameters. Next is the site class parameter against which we can specify the site class to determine the short and long period site coefficients, or we can specify them directly using the FA and FV parameters. And finally, the value of time period TL, which marks the shift from the velocity domain to the displacement domain in the response spectrum curve. Remember, we need to specify that value against the TL parameter. Now, as per clause 12.9.1.4, there is a necessity to scale up the base shear obtained from the response spectrum analysis to the value of the base shear obtained in the ELFP procedure if the latter is larger than the former. So if we have this building and we are doing a seismic analysis to the response spectrum method, we obtain a base shear. Now, we need to compare this base shear against the base shear that has been obtained in the equivalent lateral force analysis. And if the latter is bigger, the engineer would need to scale it up. And now it's time to discuss the final combinations of two orthogonal directions of earthquakes. The code has mentioned this in clause 12.5, but a very detailed understanding can be got from the commentary. Note that this discussion now is not specific to the response spectrum analysis, but would hold good for any seismic analysis to the ASCE code. So, for the structures assigned to seismic design category B, or seismic design categories C through F with orthogonal lateral load resisting systems, the interactions of the earthquake force between two lateral directions need not be considered. So, in such cases, the seismic load cases can be in the x and minus x directions, each being considered once with positive shift and once with negative shift of the center of mass for the consideration of accidental torsion. Similarly for the z direction. Thus, a total of 8 seismic load cases needs to be defined. In our demonstration section, however, we would consider the negative direction in load combination and thus having 4 load cases only. For structures which have been assigned to seismic design category C through F, but which has non-parallel lateral load resisting systems, or for vertical members, which is coupled with multiple lateral load resisting systems, the code suggests a 30% addition of earthquake force from the other orthogonal direction. However, the accidental torsion need not be considered for the earthquake direction that produces the lesser effect. In other words, the direction of the earthquake, 30% of which is considered, does not need to have the accidental torsions considered. If you remember, we had talked about an additional load case in each direction without torsion being considered, which is to be used in such 30% combination cases. Thus, this would result in the doubling of the pure earthquake combinations from 8 to 16 to give the resultant earthquake forces in the two orthogonal directions. And finally, the resultant horizontal earthquake effects are obtained from the pure earthquake combinations that we showed you before. The final horizontal earthquake effects needs to be determined by multiplying the forces with the redundancy factor from clause 12.3.4 before they are used in the strength combinations. Now we go over to the demonstration section.
So we have another poll questions for you. So you want to know which structural product you are using for your structural analysis and design purpose. So whether it is Stead or RAM structural system or any other software like ETABS, MIDAS or Sept 2000. So please cast your vote. You can select multiple products. So if you are using Stead along with RAM structural, you can select multiple products from this list. Now I will demonstrate how we can apply the response vector load based on ASCE 716 code in this Stead model. This is a 34-story concrete building. Overall height of the building is around 140 meter with maximum base dimension of 52 meter. There is a 3-story podium which mainly used for car parking and commercial purpose. My intention is to perform dynamic analysis for this building. As Shudip informed, there are several inputs that we need to specify for a response vector load case. Along with that, we need to combine the dynamic load case properly with other gravity load case. How to do that? First, I want to add a dynamic load or response vector load under a primary load case. There is no rule to specify dynamic load case under first primary load case like static seismic load. So we can add it under any new primary load case. In the response vector dialog, different versions of ASCE 7 code is listed, and for this demonstration, I will use ASCE 716 code, which is the latest one. There are few inputs which needs to be specified. First, some information about the structure which is required to determine these seismic parameters. About the mapped acceleration parameters, zip code for this site location is 92887. If you have an active internet connection, you can use this value and program automatically finds out the SS and S1 parameters from USGS site. Else, you can provide the SS and S1 values directly, which are mentioned here. Coming to the spectrum table inputs, site class for this site is B. Depending on SS and S1 values and site class information, short period and long period site coefficient values are calculated automatically from table 11.41 and 2. You can manually change the FA and FB values, but that is not required. TL value can be computed from chapter 22. Here we will use the value as 8. Now, depending on the occupancy type of this building, risk category is 3, determined from table 1.51. Seismic importance factor is 1.25 as mentioned in table 1.52. Now to calculate the seismic design category from table 11.61, we need the SDS value. This can be calculated based on the SS and SMS value, and the value comes as 1.197 if we calculate it using these formulas. For this value, seismic design category is D. The lateral load resisting system plays a vital role for structural response against seismic load, and depending on this, seismic load on the structure is calculated, which is I by R into the spectral acceleration value. For this model, it is ordinary frame and shear wall structure, and from table 12.21, we can find that the response reduction factor is 4.5. So IF by R value in either direction comes as 0.28. We need to specify this value as direction factor in both X and Z direction. We will consider only positive factor as negative directional load will be considered in the load combination cases. We are almost done with parameter specification. I am not using the missing mass correction for this model. Response spectra uses modal combination method to combine the modal responses from individual mode. There are several methods available like the CQC, SRSS or absolute method. If there is any closely spaced mode, then CQC method provide more accurate results. So I am going to use this one for this model. For this combination process, we lost the sign of the final response quantity and it is an absolute number. We can use signed response spectra with dominant mode option and program assigns the sign of dominant mode to the final response value. In our last session, we have discussed different options for the signed response spectra like the dominant mode and the signed option. So you can go through the session for more details. And coming to the torsion inputs, as Sudhir mentioned, we need to consider the accidental eccentricity value in both positive and negative direction. First, let me create a load case with accidental eccentricity value as positive 0.05 or the 5%. In next load case, we will consider this value as minus 0.05. Note that the static eccentricity remains 1 for all cases. And finally, another spectrum load case with no torsion. This load case will be used for orthogonal effect consideration. So, these three response spectra load cases are created for X direction, load 1 and 2 considering accidental eccentricity value with positive and negative factor, and load 3 without considering the accidental torsion. I need to repeat the same process for Z direction. In Z direction, three separate load cases are created. Load 4 and 5 with accidental eccentricity and 6 without any torsion value. Rest of the inputs are same except direction factor which is now specified for Z direction with value 0.28. Next, we need to generate the orthogonal cases as suggested in clause 12.5. We need to create 4 load combination cases for each direction where the respective response spectral load case will be combined with 30% load from orthogonal direction. Consider X direction. First load combination should combine load case 1, which is the response spectral load from X direction with positive accidental eccentricity value, and 30% of load 6, which is no torsion load from Z direction. Second combination is the load case 1 and 30% load case 6 from negative direction. So minus 0.3 is the combination factor. This should be repeated for load case 2 and load case 6, considering the response spectral load from X direction with negative accidental eccentricity value. 4 load combination cases are created now for load case from X direction. Same needs to be created for load from Z direction also. This time, load 4 and 5 is combined with load case 3 with factor 0.3. All total 8 load combination cases are created considering the orthogonal effects. These 8 are the final dynamic load cases that should be used in analysis and combination with other load cases. Finally, we need to combine these load combination cases with gravity load. Now, there is one very important aspect which we need to consider, the redundancy factor. As the seismic design category of this structure is D, so we need to assess the torsional irregularity for this model and accordingly determine the redundancy factor. According to clause 12.3.4.2, for seismic design category D with extreme torsional irregularity, it should be 1.3. And if the structure is torsionally stable, still it should meet two other criteria before reducing the value. So we need to first check whether the torsional behavior of this structure is okay or not. Program can check few irregularities of structure if check irregularity command is provided. From flow diaphragm option, we can select ASCE7 code and tick the check irregularities option. Note that this check is only performed if rigid flow diaphragm is specified in the model. For this command, for ASCE7 code, three irregularities are checked. First one is the torsional irregularity check. Second one is the reentrant corner check. And final one is the mass irregularity check. When you perform this check for any model, torsional behavior of the model is calculated and unit load is applied in each orthogonal direction at the center of mass of diaphragm, and displacements of the two extreme ends of the diaphragm are extracted. The ratio of this is compared with the code limit, and if the ratio exceeds the limit, that is reported in the output. In the output, the details of each irregularity check is mentioned with details. For torsional irregularity, first the displacement of each diaphragm in x and z directions are mentioned, and then the ratio is printed. It is compared with 1.2 and 1.4, which are the limits, and the status is mentioned in the table for each diaphragm. For this model, there is no torsional irregularity noticed and all diaphragms are okay. Though the structure is torsionally okay, still for safety consideration, we are considering the redundancy factor as 1.3. To consider this factor in analysis, there are two approaches. Either we can create 8 new load combination cases where the existing dynamic load case is multiplied with this factor. Else, we can use this as the combination factor for seismic load case during combining with gravity load cases. Say I want to generate a combination case as per ASCE7 code where combination factor for dead load is 1.2, live load is 1, and seismic load is 1. For this model, load 7 is the dead load case and load 8 is the live load case. To create this combination using second approach, we need to combine load 7 with factor 1.2, load 8 with factor 1, and load 11, which is the response vector load from X, with factor 1 into redundancy factor 1.3. This is the final load combination case, the result of which should be considered for member design. Same should be repeated for seismic load with combination factor minus 1.3. With this, we have considered seismic load from negative x direction. Similarly, we need to create the load combination cases for all directions. So, from 8 seismic load cases, 16 total load combination cases are created considering seismic load from both positive and negative x and z direction. Next, I want to discuss on how the dynamic analysis results are reported in the output and how to interpret the results. First, the eigensolution results are reported, frequency and time period values for each mode. Then, for each response vector load, the results are reported separately. Consider the first load case, which is the response vector load from x direction with 5% accidental eccentricity value. First, the modal weight values are reported in 3 orthogonal directions, which is the modal mass times g. For the selected modal combination method, missing weight is also reported. Next are the acceleration value for each mode and damping values. For response vector for all modes, same damping is considered. The translational and rotational component for modal base results are also reported. Next is the mass participation factor. The mass participation for each mode along with cumulative mass participation till that mode for X, Y and Z axis are reported in this table. This table is very important and we need to review the mass participation factors. I will discuss this in details. Base shear value is reported for 4 modal combination methods, though we have specified only CQC method as modal combination method. Peak story forces at each diaphragm level is mentioned next. Here, the story shear value in Z direction is 0 as the load is applied from X direction only. Next are the torsional results. The plane dimension of the floor is used to calculate the accidental eccentricity value, which is 0.05 into plane dimension in perpendicular direction of load. Then it is multiplied with story shear value to calculate the accidental torsion of that floor. All these values are reported for each story level. Note that there are 2 additional text files stored in the same folder where the story shear values and eccentricity results are reported. You can also check the dynamic analysis results from the post-processing mode. After analysis, the results are available under Dynamics tab. You can check the time period and participation factor for each mode from the table. Also, you can check the mode shapes graphically for each dynamic load case. Results for individual mode can also be checked if IMR load cases are created from response vector dialog. And finally, you can also check the animated view of the modes just to get an idea how the structure behaves depending on the applied lateral load for that particular mode. There are few things which we should check if we want to perform dynamic analysis for any model. First one is the mass participation factor. Code suggests that the overall mass participation in each direction should be at least 90%. If not, then we should consider higher modes till at least 90% mass is not considered in the analysis. We need to ensure that for this model also, whether 90% mass of the overall structure is excited for seismic analysis or not. This can be checked easily from the output file. In first response spectral load, under mass participation table, we can notice that the mass participation in X direction is 82% and in Z direction it is 79%. So for both direction 90% mass participation is not achieved. As I was saying, by default program considers 6 modes for dynamic analysis. Considering these 6 modes, 90% mass participation is not achieved and now we need to consider higher modes. This can be considered using the cutoff mode shape command. From miscellaneous commands, we can specify the desired mode number using cutoff mode shape command. Here we can specify any number and that many modes are considered for the analysis. But with increased modes, analysis time also increases. So we need to find optimum mode numbers which is required to get around 90% mass participation. Obviously, we can consider more number of modes, but normally it has been noticed that after 90% mass participation, if we consider higher modes, the change in mass participation is nominal. Now we can use the same model and increase the mode numbers. But as all load cases are considered for analysis time will also increase. If we perform 3 trials to get optimum mode number, each trial will take considerable amount of time. To reduce this, for this trial phase, we can use the same model without any load case and use modal calculation requested command which performs the eigen solution. You can say this is the first step before creating the response spectral load cases. As no other load case is present, so analysis time will be reduced. I have assigned 20 modes. Now we can check the output file, the mass participation table. Here you can notice that 90% mass participation is achieved in 11th mode for X direction and 13th mode for Z direction. Also you can find that the change in mass participation reduces as we go for higher modes. For this model, we can use 15 modes for which 90% mass participation is achieved for both X and Z direction. Now, in the original model, we can assign the same. Finally, I want to discuss another point which is important for dynamic analysis: comparison of base shear with static seismic load case. Sudeep already discussed this, and we need to compare the base shear value of response spectral load with static seismic load. If the base shear value obtained from response spectra is less than the base shear of static seismic load, then we need to find out the ratio and use it in response spectral load. How to do this? To compare this, we need to add static seismic load case. First, we need to define the seismic parameters from seismic definition window by selecting ASCE 716 code. We need to use same inputs like zip code 92887, TL is 8, importance factor 1.25, R value is 4.5 in both direction, and site class is B. We can specify CT and X values from table 12.82, or we can also skip, then program calculates the value internally. I have discussed the seismic definition part in my last webinar. You can go through the recording for more details. Now, static seismic load cases should be the first load case defined in a model. For this model, either you can create two fresh primary load cases where you can define the static seismic load and rearrange the load numbers. Or, similar to mode number selection, you can check this with the same model before defining any load case. I am using a copy of this model. First two load cases are static seismic load in X and Z direction with load factor 1 and without considering any torsion input, as that is not relevant for base shear calculation. Similarly, two spectrum load cases are added in X and Z direction with direction factor 0.28 as discussed earlier. After analysis, we can go to the output file and check the base shear values for static and response spectral loads. For static seismic load, the time period is calculated using the empirical formula using CT and X values, and if you compare it with dynamic load case, the fundamental time period is close to static load in Z but different in X direction. Base shear value for static load case is 6441 metric ton, and for response spectral load in X, it is 1745. So the ratio is around 3.6. For Z direction, the base shear is 1569 and ratio is 4.1. We need to use this as multiplication factor during response spectra definition. So in the original model, we need to multiply I by R value with this factor, which comes as 1 for X direction, and specify this as the direction factor. Similarly, for Z direction, we need to calculate the modified factor, which comes as 1.15, and specify the same as direction factor. Just one additional note. In this demonstration, I have not defined the mass model under any dynamic load case. Normally, we should define the mass model under the first dynamic load case. I have already defined a mass reference load case and specified all seismic weight under this mass reference load case. So, both for dynamic analysis and static analysis, seismic mass is considered from this mass reference load case. No need to define any further mass model or seismic weight. I have discussed in details about the mass reference load case and how to auto-generate this from dead and live load in my last webinar. You can check that session for more details. That's all from us today on response spectra analysis based on ASCE 7 code. We will cover dynamic analysis according to EC8 code in our future webinar. If you want to know more about any particular topics, post your thought in the survey window. We will try to cover that in our future session. Just a small announcement about the workshop on Stead. As you know, old select server based license system along with older V8i version of Stead will be discontinued from 1st January 2021 and everything will be moved to Connect Edition version. To smoothen the transfer process from old V8i to new Connect Edition version and to make you familiar with the enhanced feature of Stead Pro Connect Edition, we plan to deliver few free hands-on workshops on Stead Pro Connect Edition as well as on some selected topics like seismic analysis. The basic Stead Pro Connect Edition workshop will be delivered in November 2020, and if you want to join, you can cast your vote in the poll question which will be available shortly. In early 2021, we will deliver a complete workshop on advanced seismic analysis using Stead Pro Connect Edition, and the prerequisite for that session will be adequate knowledge of Stead Pro Connect Edition version. So we suggest you to join the basic workshop first if you are not familiar with the latest Connect Edition version of Stead. If you are interested, cast your vote and we will send you the registration link of the free basic workshop as soon as the date is finalized. Hope to see you all in my next session. Now, I'll open the floor to any questions you have. So once again, thank you everybody for joining the session. So we have two poll questions now. First one is about the basic workshop of Stead Pro Connect Edition. So as I was mentioning that the Connect Edition version is the latest one and you need to use this one because the V8i version will be discontinued very soon. So if you want to join the basic workshop on Stead Pro Connect Edition, please cast your vote and we will send you the registration link once the date is finalized and the registration page is generated. So please cast your vote for the basic workshop first. And next we have another poll questions that is related to the seismic analysis. So as I was mentioning from the first part of seismic series, that we are planning to deliver one full day workshop on or half day workshop on seismic analysis. Some advanced topics will be covered there like the ELA procedure, like the dynamic analysis, like how we can generate these particular load cases and everything. So those will be delivered using the Connect Edition version, and you need to be familiar with the Connect Edition version to join this particular workshop on seismic analysis. So please cast your vote if you want to join the seismic analysis as well, the workshop on seismic analysis as well. But please remember that this will be based on Connect Edition version. So please make sure that you are familiar with Connect Edition version. And if you are not, then please join the first workshop on basic Stead Pro Connect Edition. And once you are familiar, you can join this particular seismic analysis workshop on using the Stead Pro Connect Edition. So please cast your vote if you want to join the seismic analysis workshop also. So now we will move to the Q&A session. I find that there are several questions related to the seismic analysis, the dynamic analysis part. So if you have any further question, please type your question in the Q&A widget. And myself and my colleague Shudip is here. We are going to answer your questions, whatever you have. So first, I will start with Shudip. So Shudip, can you please answer the questions?
Yes. Can you hear me?
Yes, we can hear you, Shudip.
Okay, fine. So one of the questions was asked, I think, when I was presenting, and it was asked whether the torsional irregularity did not be considered in dynamic analysis. No, that is not what I said. I said that torsional amplification does not need to be calculated or needs to be done in a dynamic analysis. So basically, when you are doing a statistical analysis, you need to amplify the torsional moments. But in case of a dynamic analysis, you do not need to apply the torsional amplification. Now, I think there is just one case where you probably do not need to consider accidental torsion, and that is, the structure in seismic design category B with type 1A irregularity. That's the only case, and if it doesn't have a irregularity. But ideally, I would suggest that you need to consider the accidental torsion, and for all the cases, the only thing is that you do not need to consider the torsional amplification. So that's one of the question. The other question was, okay, so is there any code requirement that doesn't allow for torsional mode in the first two modes? I haven't honestly found any such clauses or any such requirements in the ASCE code, but that's a very good question. I would, it would be ideally suggested that your first two modes be translational modes instead of torsional mode. If your first mode ends up to be a torsional mode, then there is high chances that that structure would be classified as extremely torsionally, and that would need additional fixing. So I think it's the best way to go ahead is to ensure that the first two modes at least are the translational modes, and we have, and if you do not have translational modes, torsional mode precedes that, then it would mean that your structure is torsionally flexible, and chances are that is extremely torsionally irregular. The next question was, is it okay if 90% mass participation is not achieved in the y direction? Now, this is a very good question in the first place. One of the things that happens now if you consider a building structure like the one that we showed, the vertical direction generally turns out to be a high stiff direction. So it is difficult to attain a 90% participation in that direction. That is agreed. But there can be situations where if you have very large spans, which would mean that there is a chance of vertical vibration, you probably will start seeing, you probably won't get much of a difficulty in attaining mass participation in the vertical direction. On the other hand, if you do want to consider the mass participation in the vertical direction, and it's a stiff direction, the vertical direction is a stiff direction, then one thing that you could check is whether the frequency of the vertical modes is over 20 hertz. That would mean that it's basically a static mode. That is, you do not actually need to do a dynamic analysis for that mode. Or in other words, the torsional or the dynamic amplification will not be possible in that mode. So you can actually consider those modes as the missing mass modes, and statically add that to the response spectrum analysis that you have obtained the structure. So basically, in short, the answer is, if you want to have participation in the y direction, you need to see if before you obtain the y direction participation, or the modes where you have started getting the y direction participation, if it's over 20 hertz, if it is, then you consider that as a missing mass mode. The 90% requirement, as I understood from the code, was mostly for the lateral direction. Okay, so those are the three questions that I answered. Surajit, is there any other question that you want me to answer?
Yes, there is another one. So there are so many questions there. So the next question is, after changing the direction factor using static base shear, will the ratio will again change after changing the direction factor? So, so can you please answer this one also, Sudip?
Okay, so basically, see, if it's the chances are that it will not happen, because unless you are changing the stiffness and the mass properties of the structure, the participation would remain the same. So um, unless you go ahead and change the mass distribution or the stiffness distribution, you do not need to do that again. It would be the same. So it's only once that you need to consider the scaling factor. I think it's about the scaling factor, right, Surajit? I didn't see the question.
Yes.
Okay,
This is
so
about the
basically,
scaling factor.
right. So basically, then you are doing a static seismic analysis and a dynamic analysis. Your response spectrum analysis ends up with lesser base shear, and you calculate that scale factor. So unless you change the mass and the distribution, the mass distribution and the stiffness factors, or the mass distribution or the stiffness distribution, the base shares is expected to remain the same. So I don't think you would need to change the scale anymore.
Okay, so I am taking the next question, that are there any special consideration to be taken care when we are designing steel structure for seismic design? So the analysis part is same, but for a different steel design code like the AISC code, AISC 360 code, or the Indian code IS 800, or for the EC8 code. So there are several there are several part of the code which refers to the ductile detailing part. So, like for the AISC code, there is a separate code available that is only based on the ductile detailing or the seismic provision check with seismic parameters. For Indian code, there is a chapter 12, which refers to the special seismic design criteria. So, if you want to design your steel structure based on your seismic analysis results, then you need to consider this part also. So, you need to consider the guidelines provided in these particular codes for the steel design part for with seismic design criteria. So that needs to be considered. Okay, so next we have another question, is that do we have to consider orthogonal effects when performing the dynamic analysis? So should you answer this one?
Yes, so there are, you do need to consider the orthogonal effects. The code actually has suggested uh, if you reprieve, so basically then if you are having, say, seismic design, so if you are having the structure which has been assigned a seismic design category B, C through F, and you have an orthogonal system of lateral load resisting system, then you do not need to consider the orthogonal effects as such. But in cases of specific seismic design category C through F, where you have a non-parallel lateral load resisting system, or for members that forms part of multiple frames that resist the seismic load, you need to consider uh, the combination effect. So I think in that sense, you would end up, it would be very difficult to isolate one single member for this combination. So I would suggest in cases, if you're having the appropriate seismic design category C through F, you do consider, irrespective of whether you have a non-parallel or a non-parallel load resisting system, you do need to consider the orthogonal effects.
Uh, okay, so I am taking the next question, is that do we need to make a separate model to calculate the V based on ELF procedure when scaling? So it depends on you. You can put the static seismic load case in the same model where you have defined the response vector or the dynamic load case along with your dead and live load cases, and also the wind load cases. And after the first trial, you can just use the scale factor in the response vector load cases. You may also inactive the static seismic load cases also. So if you want to just reduce the analysis time for the static seismic load case, but that totally depends on you. If you want, you can just use a separate model, means the same model with the basic load cases only, the static, seismic, and the dynamic load case, and find out the scale factor from there. Or if you want, you can also put that static seismic load case in the same model that you are using for the analysis and the design purpose. So that depends on your requirement. There is another question, is that are the loads will be applied in three directions, X, Y, and Z. So as Sudeep is mentioning that we can put the vertical, we can consider the vertical load effects of the dynamic load case. So that depends on your requirement and how the codal provisions are mentioned about this one. But for this example, actually, we have shown the X and Z directions only. But similarly, you can consider the Y directions.
So basically then in the workshop, because we could see that there are so many questions that relates to the vertical vibrations. In the workshop, we would include the vertical vibration, the example of the vertical vibration as to how we need to go and do that.
Okay, so we are almost done. So there is one question, is that software support UBC 97 response spectrum? So yes, I think we have the option, but the UBC 97 is very old. So, but still it is there, I think. So if you want to use the latest one, then the ASCE 716 code, then you need to use the connect edition version because it was not implemented early in the earlier version. But if you want to use the older one, 97 version, it is still available there. And the final question I can take is that about the load combination, it can generate load combination automatically. So I'm not sure what you are referring to, but if you want to use the auto load combination to generate the seismic load combination cases automatically, then also you can do that one. But for that, you need to modify the load combination or the auto load combination rules a bit so that it will consider the seismic load cases properly. But it can be done. Final one is that, is it possible to add seismic load cases in the repeat load case while doing static analysis? Yes, actually we have shown the combination cases here, the load combination, but in similar fashion, you can create the repeat load cases also. For example, if you want to perform the direct analysis or the P delta analysis with KG matrix, then you need to create, generate the load cases using the this particular repeat load cases. So load combination cases are not allowed in such cases. So in I have shown in my demonstration process, I have shown the combination cases, but similarly, you can recreate the same combination cases using the repeat load command. So that is actually possible. Okay, so Sudeep, you want to answer any further thing, or if you want to add any further thing? So we are done with the Q&A session.
Yeah, I think the repeat loads, in one sense, is not. If you're using a static seismic analysis, you can use the repeat loads. For that, you need to specify the perform analysis and change command. Though that is probably not required under the current, in the current Connect edition. But I'd still suggest that you go and do a perform analysis and change command after each static seismic code case if you want to intend to use the repeat load cases. For response spectrum, we do not have a way of considering that as a repeat load right now, partially because of the nature of the repeat load case in itself. So in that case, we have to do that with load combinations.
Okay, so we are done with the Q&A sessions. But please remind that if you later access this particular webinar as an on-demand session, and if you have any further questions, you can also put that in the Q&A window. So we always access this particular Q&A session window and try to find out if there is any new questions or not. So if there is any new query, we'll obviously send you the answer via email. So thank you everybody, and if you want to join the workshops, please let us know via the survey or the poll questions link, and we will send you the registration link as soon as the event is created and we have the finalized date with the registration link. And we hope to see you all soon, very soon. Please remember that we have a year in infrastructure award that is from 20 and 21 of October. If you want to join, it is now live, means the registration is live now. If you want to join, you can register. And you can just access the session on 20 and 21st of October. So thank you, everybody. I hope to see you all soon in my next session. So thanks.
Yeah, thank you.